Welcome to the Explainer. Today, we are tackling what's honestly one of the most frustrating bottlenecks in modern AI development right now. Look, if you're building with vision models, you absolutely know the pain we're talking about. The image processing capabilities, incredible. But those token costs, they will literally drain your budget dry. So today, we're taking a really close look at Headroom's image compression. It's this fascinating, absolute game-changer of an approach for developers who are just struggling to scale. We're going to break down exactly how it works and show you how it saves massive amounts of tokens without sacrificing an ounce of accuracy.
Okay, let's dive right into this. Think about this number for a second. 765. That right there is the token cost for sending just one single 1024 by 1024 pixel image to OpenAI. Just one. Now, zoom out a bit. If your app is processing thousands or maybe millions of images a day, those 765 tokens per image compound into a massive, massive financial burden. Raw image processing at scale is heavy, it's slow, and most importantly, it is incredibly expensive.
So here is our roadmap for today's explainer. First, we'll cover the vision token problem. Second, the smart ML router. Third, adaptive compression techniques. Fourth, savings by provider. Fifth, under-the-hood performance. And finally, zero-code integration.
All right, kicking things off with part one, the vision token problem and balancing cost versus accuracy.
So, how do we actually cut these costs without losing accuracy? This is the ultimate developer dilemma, right? Vision models charge you by the token. You want to scale, so obviously you need to reduce those tokens, ideally by somewhere between 40 to 90%. But here's the catch. If you just aggressively blind compress every single image, the AI model loses those crucial tiny details it actually needs to answer the user's prompt correctly. So the million-dollar question is, how do you compress an image dramatically without basically lobotomizing the AI's ability to see what it needs to see?
Which brings us to part two, the smart ML router and intelligent compression.
Now, what's really interesting about this is exactly how Headroom approaches the problem. It doesn't just treat all images equally. Instead, it uses a mini LM classifier router. You can think of it like an incredibly fast, highly intelligent traffic cop that sits right between your user and the vision model. It actively reads the prompt, analyzes exactly what the user is asking the AI to do with that specific image, and then dynamically selects the absolute best compression technique for that exact request.
And look, this isn't just your basic run-of-the-mill keyword matching. This router is a fine-tuned mini-LM classifier that was actually trained on over 1,000 examples, 1,157 to be exact. It understands context. It intrinsically knows that what the AI needs to see to answer a really general question is vastly different from what it needs to see to answer a highly specific, detailed question.
Moving right along to part three, adaptive compression techniques. Let's look at these tailored techniques.
The strategy here is actually remarkably clear. The router has an arsenal of four main adaptive techniques. First up, full low. This gives you a massive 87% savings when the user just needs general understanding. But look right below that at preserve. The router is actually smart enough to completely pivot to 0% savings when absolute, pixel-perfect fine details are required. Then you've got crop for region-specific queries, which saves you 50 to 90%. And finally, transcode. This one translates images directly to text for a staggering 99% savings when the prompt is literally just about extracting text.
And this brilliantly illustrates why context matters so much. Just imagine you upload a picture of a cat. If your prompt is describe the scene, well, the router instantly applies that full load technique. The AI can easily tell it's a cat in a room even if the image is heavily compressed, right? Boom, you just saved 87% of your tokens. But if your prompt is count the whiskers, the router recognizes that microscopic detail is absolutely required here. It automatically switches over to preserve, keeping the full resolution so your AI doesn't hallucinate the answer.
Okay, part 4, savings by provider. Let's look at some massive token drops.
Let's start things off with Anthropic. For a 1024 by 1024 image, we are looking at a really dramatic drop. Before Headroom, you're spending roughly 1398 tokens. After the router does its thing and optimizes it, you're down to just 349 tokens. Guys, that is a 75% reduction. Headroom pulls off this specific optimization for Anthropic by utilizing a pile-based resize down to 512 pixels whenever fine details aren't strictly needed.
Now, what about Google Gemini? Again, we see a massive 75% drop. It takes a large 1536 by 1536 image from 1,032 tokens all the way down to just 258. You might be wondering, why those specific numbers? Well, it's because Headroom optimizes specifically for Gemini's underlying architecture. Gemini uses a 768 by 768 tile system. So by intelligently resizing it, Headroom reduces the image from taking up 4 tiles down to just one single tile. And here is the breakdown for OpenAI leveraging their native detail parameters. When the smart router decides that the full low technique is the way to go, it drops that painful 765 token cost down to a mere 85 tokens. That's an absolutely incredible 89% savings. But again, the real magic here is in the safety net, right? Because when preserve is needed, it just leaves it at 765. It ensures your AI's accuracy is never, ever compromised just for the sake of cheapness.
Part 5. Under the Hood Performance. Let's talk metrics. So the crucial point is, if you're a skeptical engineer watching this, you are almost certainly wondering about latency. Is this going to bog down my app? Well, the latency penalty is practically non-existent. Check this out. The router inference takes roughly 10 milliseconds on a CPU, and an astonishingly fast 2 milliseconds on a GPU. The image resizing takes between 5 and 20 milliseconds. You are literally adding fractions of a second to your request. Meanwhile, this highly efficient, totally lightweight 128 megabyte model is making the correct routing decision 93.7% of the time. It's incredibly fast and it's remarkably accurate.
Finally, Part 6, Zero-Code Integration, the plug-and-play proxy.
Let's move to and see how this actually builds into your workflow. You can use Headroom's client or direct API, sure, but perhaps the most interesting method, the real mic drop here, is the Headroom proxy server. When you route your traffic through their proxy, image compression happens automatically on every single request that contains images. Your application just talks to the proxy exactly like it already talks to OpenAI or Anthropic. It requires absolutely zero code changes to your core application logic. Zero. It's basically a complete plug-and-play cost reducer. Which leaves us with this final thought for today. Vision models are unlocking some truly incredible capabilities for us right now, but cost has almost always been the leash holding developers back. So think about this. If you implement this proxy server tomorrow, and you automatically slash your vision token usage by up to 90% in a matter of 2 milliseconds, what previously too expensive features can you now actually afford to build? What new level of scale can your application achieve? It really is a fascinating paradigm shift for AI development. Thank you so much for joining me on this explainer, and I genuinely hope this helps you build faster, smarter, and way more cost-effectively.